Right now, at this very moment, you're living on a planet that circles a star, and that star is accompanied by the most magnificent collection of worlds you could possibly imagine. One of those worlds, Saturn, wears a crown of ice and rock so spectacular that when humans first glimpsed it through telescopes, they thought their eyes were playing tricks on them. Everything you think you know about those rings, their ancient permanence, their eternal dance, isn't quite what it seems. Welcome to Sleep About Science. Tonight, wherever you are in the world, we're traveling back to witness one of the most beautiful catastrophes in our solar system's history. The day Saturn got its rings, and if you drift off to sleep while listening, that's perfectly wonderful. The cosmos will continue its ancient dance, whether you're awake or dreaming. Before we begin, please make yourself comfortable. Pull up those blankets, adjust your pillow, let your breathing slow, and remember, this is educational content, not medical advice. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into the farthest reaches of space and time. There's something deeply soothing about cosmic stories, don't you think? The universe has been unfolding its dramas for billions of years, and tonight we get to witness one of its most spectacular performances. Now, imagine you could step outside of time itself, floating in the darkness between stars, watching our solar system not as it is today, but as it was roughly 4 billion years ago. The sun burns younger and more violently. The planets dance in orbits, still settling into their eternal rhythms, and Saturn, magnificent Saturn, looks nothing like the ringed jewel you know today. It's a lonely giant, spinning in the cosmic dark, naked of the crown that will one day make it the most beautiful world in our solar system. This is the story of how that crown came to be. This is the story of cosmic violence transformed into cosmic beauty. This is the story of the day Saturn got its rings. But let's start even further back, shall we? Let's begin with the formation of our solar system itself, roughly 4.5 billion years ago. Picture a vast cloud of gas and dust, so enormous that it would take light thousands of years to cross from one side to the other. This cloud, what astronomers call a molecular cloud, has been drifting through space for millions of years, cold and dark and seemingly lifeless. The cloud is ancient beyond human comprehension. It has watched the birth and death of countless stars, has been sculpted by stellar winds, and enriched by the explosive deaths of massive suns. Within its dark folds lie the remnants of stellar nucleosynthesis, oxygen forged in the hearts of dying stars, silicon created in the fury of supernovas, iron scattered by stellar explosions, so violent they outshine entire galaxies. This cloud carries within itself the chemical legacy of cosmic history, the elements that will one day form planets and moons, and eventually thinking beings who will wonder about their own origins. But something happens. Perhaps a nearby star explodes in a supernova, sending shockwaves rippling through space at speeds that dwarf anything in human experience. Perhaps the cloud passes too close to another stellar nursery, where young, hot stars are blowing fierce stellar winds. Perhaps it's something even more subtle, the gravitational influence of a passing star cluster, or the density waves that propagate through our galaxy's spiral arms. Whatever the trigger, gravity begins to win its ancient battle against the random motions of gas molecules. The cloud begins to collapse. This collapse is not violent or sudden. It unfolds over millions of years with the patience of geological time. But as it happens, something beautiful occurs. As the cloud collapses, it spins faster, just as a figure skater spins faster when they pull their arms close to their body. This is conservation of angular momentum, one of the universe's most fundamental principles. The cloud flattens into a disk, and at its center, matter presses together with increasing force. Temperature begins to rise at the cloud's heart. What was once cold, dark matter becomes warm, then hot, then blazingly hot as gravitational potential energy converts to thermal energy. Pressure mounts. Nuclear particles that have existed separately for millions of years suddenly find themselves pressed together with enormous force. And then, in a moment that transforms the entire system, nuclear fusion ignites. Hydrogen nuclei overcome their mutual electrical repulsion and fuse together, releasing energy in a burst of light and heat that sweeps across the forming solar system. Our sun is born, blazing to life, like a cosmic lighthouse, suddenly illuminated in the darkness. Its light races outward at the speed of light, 299,792,458 meters per second, carrying energy that will warm worlds not yet born and power processes not yet imagined. The young sun is more violent than the gentle star we know today. Solar flares erupt from its surface like cosmic tsunamis. Stellar winds blow with hurricane force, carrying away much of the remaining gas in the solar system's inner regions. In this disk of leftover material, what astronomers call the protoplanetary disk, something remarkable is happening. The same forces that created the sun are now at work on a smaller scale throughout the system. Tiny particles of dust and ice, no larger than the particles in cigarette smoke, are sticking together through electrostatic forces and weak gravitational attraction. This process, called accretion, is slow and patient. Grain by grain, these cosmic building blocks accumulate. Dust particles stick together to form fluffy aggregates. These aggregates collide and merge to form larger chunks. Over thousands of years, the chunks become pebbles. Over millions of years, the pebbles become boulders. Over tens of millions of years, the boulders become kilometer-sized objects called planetimals. These planetimals are the building blocks of worlds. In the inner solar system, where the young sun's heat has boiled away most of the water and other volatile compounds, they're made primarily of rock and metal, silicates and iron and nickel, materials that can withstand high temperatures. But in the outer reaches of the system, beyond what astronomers call the frost line, water can freeze and remain solid. Here, the planetimals are made not just of rock and metal, but of vast amounts of ice, water ice, methane ice, ammonia ice. This makes all the difference. In the outer solar system, where ice can survive, there's simply much more material available to build worlds. The planetimals grow enormous, becoming what we call planetary embryos. Their gravity strengthens as they grow, allowing them to attract and capture not just solid material, but the hydrogen and helium gas that still fills much of the solar system. Saturn is one of these giants. Fed by the endless supply of ice and rock in the outer solar system, it grows to enormous size with remarkable speed. Within just a few million years, which is remarkably fast in cosmic terms, Saturn has become a gas giant with a mass 95 times that of Earth. Its core, made of rock and ice and compressed to incredible densities, is surrounded by thousands of kilometers of hydrogen and helium gas compressed to liquid form by the immense pressures. The young Saturn is a magnificent world. even without its future rings. Its distinctive low density, so low that it would float in a cosmic ocean if such an ocean could exist, to comes from its composition. Unlike the inner rocky planets, Saturn is made mostly of the lightest elements in the universe. Its atmosphere extends smoothly from gas to liquid to an exotic form of metallic hydrogen deep in its interior. Storms the size of Earth rage in its upper atmosphere. Lightning bolts thousands of times more powerful than terrestrial lightning flash between its clouds. But Saturn is not alone in its formation. The same processes that built the giant planet are also at work in the disk of leftover material that surrounds it. Around Saturn, in this swirling disk of gas and dust and ice, dozens of moons are taking shape through the same accretion process that formed the planet itself. Some of these moons are tiny, irregularly shaped chunks of rock and ice that barely deserve the name moon at all. They're more like large asteroids, captured by Saturn's growing gravitational influence and held in distant, elongated orbits. Others grow to substantial size, becoming worlds in their own right, with their own geological processes, and in some cases, their own satellite systems. These larger moons are remarkable worlds. There's Titan growing to become larger than the planet Mercury, developing a thick atmosphere rich in nitrogen and organic compounds. There's Enceladus, a small world that will one day harbor a global ocean beneath its icy crust. There's Iapetus, with its mysterious two-toned coloring and towering equatorial ridge. There's Rhea, Dione, Tethys, each a unique world with its own story to tell. These moons settle into orbits around Saturn, creating a miniature solar system with the giant planet at its center. Their orbits are determined by the same gravitational forces that govern planetary motion, the balance between their orbital velocity and Saturn's gravitational pull. Some orbit close to Saturn, completing their circuits in just hours or days. Others orbit farther out, taking weeks or months to complete a single revolution around their parent planet. But there are other forces at work as well. The moons exert gravitational influences on each other, creating a complex web of interactions that will slowly but inevitably change their orbits over time. Some moons become locked in gravitational resonances, where their orbital periods are simple ratios of each other, moon completing exactly two orbits for every one orbit of another, or three orbits for every two. These resonances can be stabilizing, keeping moons in predictable long-term stable orbits, but they can also be destabilizing, gradually pumping energy into a moon's orbit and causing it to migrate inward or outward from Saturn. The gravitational environment around a giant planet is complex and dynamic, full of subtle forces that can accumulate over millions of years to produce dramatic changes. For hundreds of millions of years, though, Saturn's system remains relatively stable. The planet and its moons dance their stately orbits, held in their paths by the delicate balance between gravitational attraction and orbital motion. The largest moon's Titan, with its thick atmosphere and methane lakes, Enceladus with its hidden ocean, Iapetus with its mysterious ridges, all trace their predictable paths around their parent planet. If you could visit this ancient version of our solar system, Saturn would be instantly recognizable as a gas giant. Its distinctive banded appearance, created by high-speed winds in its atmosphere, would already be apparent. Its hexagonal storm at the North Pole, Maya Duffer, weather patterns so strange that modern scientists still don't fully understand it, might already be raging, but something would be missing. Something that makes Saturn unique among all the worlds in our solar system. There would be no rings. The Saturn of 4 billion years ago was a magnificent world, but it was a naked giant spinning in the cosmic dark. Its moons orbited in empty space, unmarked by the brilliant crown of ice and rock that makes modern Saturn the most beautiful planet in our solar system. The space between Saturn and its moons was filled with nothing more than the thin wisps of hydrogen and helium that still pervade the outer solar system. This ringless Saturn persisted for hundreds of millions of years. During this time, life began to evolve on the distant Earth. Simple, single celled organisms learned to harness the energy of sunlight through photosynthesis, gradually changing Earth's atmosphere and setting the stage for more complex forms of life. The solar system settled into the stable configuration we know today, with planets following predictable orbits around the Sun. But stability in the cosmos is often temporary, and roughly 4 billion years ago, something began to go wrong in Saturn's peaceful family of moons. The seeds of destruction lay in the very forces that had created the system in the first place. Gravitational interactions between moons, which had initially helped establish stable orbits, began to accumulate small changes over immense periods of time. Think of it as a cosmic version of the butterfly effect. Tiny influences, negligible on human timescales, gradually building up to produce large scale changes over millions of years. Picture one of Saturn's larger moons. Let's call it the Lost Moon, for reasons that will soon become tragically clear. This moon is substantial, perhaps half the size of our own moon, with a diameter of roughly 1,700 kilometers. It's made primarily of rock and ice and metals, with a composition similar to many of Saturn's current moons. It has a solid rocky core surrounded by a thick mantle of water ice, and its surface is scarred by billions of years of impacts from asteroids and comets. This lost moon has orbited Saturn faithfully for hundreds of millions of years, locked in a gravitational dance that seemed as permanent as the stars themselves. Like most large moons, it has become tidally locked to Saturn, always keeping the same face toward its parent planet, just as our moon does with Earth. If there were oceans on its surface, which there might have been in the early days when radioactive decay in its core kept it warm, they would rise and fall in eternal tides caused by Saturn's immense gravitational pull. The lost moon is not alone in its orbit around Saturn. It shares the space near Saturn with numerous other moons, each following its own path through the complex gravitational environment. Some of these moons are smaller, mere chunks of rock and ice captured from the outer reaches of the solar system. Others are comparable in size to the lost moon itself, substantial worlds with their own geological histories. But the cosmos is more dynamic than it appears to casual observation. Over millions of years, the gravitational influences of these other moons begin to have a cumulative effect on the lost moon's orbit. Like a cosmic game of billiards played in slow motion, these gravitational tugs gradually change the lost moon's orbital parameters so slowly that if you could watch from nearby, you would see no change from day to day, or even from century to century. But the change is there, inexorable and patient as geological time itself. The process is called orbital decay, and it can be triggered by various mechanisms. Perhaps the lost moon becomes caught in a gravitational resonance with one of Saturn's other large moons, where repeated gravitational tugs slowly drain energy from its orbit. Perhaps it's affected by tidal forces from Saturn itself, the same forces that keep the moon tidally locked, also gradually slow its orbital motion, causing it to spiral inward. Perhaps it's the cumulative effect of countless tiny impacts from space debris over millions of years, each impact removing a tiny amount of orbital energy. Most likely, it's a combination of all these factors. The gravitational environment around a massive planet like Saturn is extraordinarily complex, with dozens of moons and countless smaller objects all exerting their own tiny influences. Over the vast timescales involved, these tiny influences can accumulate to produce dramatic results. The lost moon's orbital decay takes an enormous amount of time. Millions upon millions of years pass as the moon's orbit gradually shrinks. If you could compress this entire process into a single day, for most of that day, nothing would seem to be happening at all. The moon would appear to orbit normally, its path seemingly stable and eternal. The changes would be so subtle that they would be virtually impossible to detect without precise measurements over very long periods. But gradually, inexorably, the lost moon spirals closer to Saturn. Its orbital period shortens. What once took weeks to complete now takes slightly less time. Its apparent motion against the background stars slowly accelerates. If there were astronomers on Saturn's other moons, which there weren't, they might eventually notice that the lost moon's position didn't quite match their ancient star charts. As the lost moon moves inward, it begins to encounter something invisible, but absolutely crucial to our story. This is what astronomers call the Roche limit, named after the French mathematician Édouard Roche, who calculated this critical distance in the 1800s. But the phenomenon itself is as old as planets and moons, as fundamental to celestial mechanics as gravity itself. The Roche limit represents the distance from a planet where the planet's tidal forces become stronger than a moon's own gravity. It's not a physical barrier. There's nothing there that you could see or touch. Instead, it's a mathematical boundary, a point in space where the forces that hold a moon together are perfectly balanced by the forces trying to tear it apart. To understand this concept, imagine holding a moon in your hands, not a real moon, which would be impossible, but a scale model made of clay. The clay holds together because of internal cohesive forces, just as a real moon holds together because of its own gravitational attraction. Every atom in the moon pulls on every other atom, creating a net inward force that keeps the moon intact. Now imagine stretching that clay moon between your hands. As you pull, you're applying external forces that oppose the internal cohesive forces. Pull gently, and the moon maintains its shape, but pull too hard, and the moon will deform and eventually break apart. The external forces overcome the internal forces that hold it together. The Roche limit works exactly the same way, except that the external forces are tidal forces created by the difference in gravitational attraction across the moon's diameter. When a moon orbits close to a massive planet, the planet's gravity pulls more strongly on the side of the moon that's closer to it than on the side that's farther away. This difference in gravitational pull creates tidal forces. You experience a gentle version of these tidal forces every day, although you probably don't notice them. The moon's gravity pulls slightly more strongly on the side of Earth that faces it, creating our ocean tides. But Earth is large enough and far enough from the moon that these tidal forces are manageable. They move water around, creating high and low tides, but they don't threaten to tear our planet apart. The situation becomes much more extreme when a smaller moon orbits very close to a much more massive planet. As the moon crosses the Roche limit, the planet's tidal forces become stronger than the moon's own gravitational self attraction. The forces trying to tear the moon apart overcome the forces trying to hold it together. For the lost moon, this moment represents the end of hundreds of millions of years of existence as a coherent world. It has survived the violence of the early solar system, the bombardment by asteroids and comets, the gradual cooling and geological evolution that shaped its surface features. It has orbited Saturn through cosmic seasons that lasted millions of years, through the slow brightening of the sun and the gradual evolution of the solar system as a whole. All of that is about to end. The lost moon begins to cross the Roche limit. And at first, nothing seems different to a hypothetical observer. The moon still looks whole and solid, its surface still scarred by billions of years of impacts, but otherwise intact. It still rotates slowly as it orbits, still maintains its tidally locked orientation with one face always towards Saturn. If there were any remaining atmosphere, which there probably isn't, given Saturn's strong gravitational field and the moon's relatively small size, the weather patterns would continue as they have for millions of years. But stress is building within the moon's structure, deep beneath the surface, in the solid rock and ice that have held together since the moon's formation. New forces are making themselves felt. The rocks and ice that have maintained their positions relative to each other for hundreds of millions of years begin to experience forces they were never designed to withstand. The side of the moon facing Saturn feels a stronger gravitational pull than the side facing away from Saturn. This difference in force, small as it might seem when measured in human terms, begins to stretch and deform the entire world. Imagine stretching a rubber ball by pulling on opposite sides, except that in this case, the ball is a world made of solid rock and ice, and the forces doing the stretching are gravitational fields strong enough to hold planets in their orbits. Cracks begin to appear on the moon's surface. These aren't the simple impact craters that have marked the moon's face for eons, caused by collisions with asteroids and comets. Instead, these are tectonic fractures, long, deep cracks that run for hundreds or thousands of kilometers across the moon's surface. They appear first in the moon's weakest areas, where previous impacts or geological processes have created zones of structural instability. As the tidal forces intensify with each orbit, these cracks grow and spread. They branch and interconnect, creating vast networks of fractures that divide the moon's surface into ever larger blocks of material. What was once a unified geological structure begins to break down into discrete chunks, each held to its neighbors only by whatever strength remains in the increasingly stressed material. Deep inside the moon, similar processes are occurring. The core, compressed and heated by billions of years of gravitational pressure, begins to experience differential forces as well. Different parts of the core feel different gravitational attractions, creating internal stress patterns that the moon's structure cannot accommodate. Internal fractures begin to propagate upward from the core toward the surface, meeting the surface fractures propagating downward. The moon's internal structure, which has remained stable for hundreds of millions of years, begins to buckle and fail. Mountain ranges that once seemed permanent features of the landscape begin to shift and collapse as the bedrock beneath them becomes unstable. If there were any remaining geological activity, volcanism, for example, or tectonic motion, it would accelerate dramatically as the moon's internal structure reorganizes itself under the influence of the overwhelming tidal forces. And then, in a moment that would be spectacular beyond imagination, if anyone were there to witness it, the lost moon reaches the point where its own gravity can no longer hold it together against the tidal forces from Saturn, the cohesive forces that have kept this world intact for hundreds of millions of years are finally overcome by the destructive forces generated by Saturn's immense gravitational field. The lost moon begins to break apart and doesn't happen all at once, like a balloon popping or a glass shattering. The destruction of a world is a more gradual and complex process. Instead, it's more like watching a mountain slowly crumble, but accelerated and magnified to planetary scale. The largest chunks of material membrane pieces that might be tens or hundreds of kilometers across separate first, breaking away from the main body of the moon along the major fracture lines that have been developing. These largest fragments don't immediately disintegrate further. Each piece is still large enough that its own gravity provides some structural integrity, but they're no longer part of a single unified world. Instead, they're independent objects, each following its own slightly different orbit around Saturn. The gravitational field that once held them as part of a single moon is no longer strong enough to keep them together. Smaller chunks follow sheer for pieces the size of mountains, of city blocks, of buildings. As the main body of the moon disintegrates, these smaller fragments are freed from the gravitational grip of their parent world. Some break away from the largest chunks, which are themselves breaking apart into still smaller pieces. Others separate directly from what remains of the moon's core. The process accelerates as it continues. As the moon breaks into smaller and smaller pieces, each piece has less gravitational self attraction to hold it together against the tidal forces from Saturn. Pieces that might have remained intact as part of a larger moon quickly disintegrate into still smaller fragments when they become independent objects. Within days, perhaps weeks, and most briefly, what was once a solid world, 1,700 kilometers in diameter, has become a stream of debris ranging in size from continent sized chunks down to pebbles and dust. The moon is gone, transformed from a single coherent body into countless separate pieces, each following its own independent orbit around Saturn. But these pieces remember where they came from. They continue to trace the same general orbital path that their parent moon once followed. The stream of debris forms a rough ring around Saturn at the distance where the lost moon once orbited. It's not yet the elegant, organized ring system we see today. It's more like a scattered cloud of tumbling fragments, each piece rotating and colliding with its neighbors in a chaotic dance of destruction. The immediate aftermath of the moon's destruction would be a spectacular sight if anyone were there to observe it. Imagine watching from one of Saturn's more distant moons as the stream of debris spreads along the lost moon's former orbital path. At first, the fragments would be clustered together, following nearly identical orbits, but even small differences in their initial velocities would cause them to gradually spread out over time. The largest chunks, the ones that were once mountain ranges or sections of the moon's crust, would tumble slowly through space, their irregular shapes causing them to wobble and spin unpredictably. Sunlight reflecting off their icy surfaces would create a glittering display as they rotated, each piece catching and reflecting light in its own unique way. Smaller debris would be more numerous, but less individually visible. Chunks the size of boulders, cars, or basketballs would fill the space between the larger pieces, creating a dense swarm of material that would shimmer and sparkle as countless small fragments reflected Saturn's pale yellow light. The finest debris, the particles, no larger than sand grains or dust motes, would form clouds so dense they might be visible as hazy, glowing streams stretching along the moon's former orbit. But this is only the beginning of our story. The destruction of the lost moon has created the raw material for Saturn's rings, but those rings won't achieve their current elegant organization for millions of years to come. The chaotic cloud of debris must first undergo its own evolution, shaped by the same gravitational forces that destroyed the moon in the first place. Over the following thousands of years, this ring of debris begins to evolve and organize itself. The pieces don't all stay in exactly the same orbit as their parent moon. Even tiny differences in their initial velocities, caused by the violence of the breakup process, lead to small but significant differences in their orbital paths. Some fragments, given slightly more velocity during the breakup, move to higher orbits farther from Saturn. Others, slowed by the breakup process or by collisions with other fragments, spiral inward toward lower orbits closer to the planet. Still others maintain orbits very similar to the original moon's, but with slightly different shapes, more elliptical rather than perfectly circular, or tilted at small angles to Saturn's equatorial plane. These orbital differences lead to frequent encounters between fragments. Pieces in different orbits move at different speeds and follow different paths, leading to inevitable collisions. When fragments collide at the orbital velocities involved peak, typically several kilometers per second, the results depend on the sizes and compositions of the colliding objects. When two small fragments collide, they might stick together if their relative velocity is low enough and if they're made of materials that can absorb the impact energy. Ice is particularly good at this means it can deform and compress during collisions, allowing fragments to merge rather than shatter. Over time, some of the debris from the lost moon begins to reaccumulate into larger chunks through this process. But more often, especially when larger fragments are involved, collisions result in further fragmentation. When two boulder sized chunks of ice and rock collide at several kilometers per second, the impact energy is enormous, equivalent to detonating tons of high explosives. Both objects shatter into hundreds or thousands of smaller pieces, adding to the population of debris and increasing the likelihood of future collisions. This collisional evolution continues for thousands of years. The largest remnants of the lost moon gradually break down into smaller and smaller pieces. At the same time, some of the smallest debris begins to stick together, forming new, loosely bound aggregates. The size distribution of particles in the evolving ring system slowly shifts towards smaller sizes as the destructive effects of high velocity collisions outweigh the constructive effects of gentle accretion. But collisions do more than just change the sizes of ring particles. They also help organize the ring system structurally. When particles collide, they typically lose some of their orbital energy. This energy loss causes their orbits to become more circular and more closely confined to Saturn's equatorial plane. What starts as a three-dimensional cloud of chaotically tumbling debris gradually flattens into a thin, organized disk. The process is similar to what happens when you shake a box of mixed objects. Over time, the objects tend to settle into layers based on their physical properties. In Saturn's forming rings, collisional damping causes the debris to settle into the orbital configuration with the lowest possible energy, which turns out to be a thin disk lying in Saturn's equatorial plane. This flattening process takes thousands of years to complete. Gradually, the chaotic three-dimensional swarm of debris transforms into something that begins to resemble the modern ring system we know today. The disk becomes thinner and more organized. Particles that once followed wildly different orbital paths begin to move in more similar, more predictable orbits. As this organization proceeds, the gravitational influence of Saturn's surviving moons begins to make itself felt more strongly. These moons, which initially had little effect on the chaotic swarm of debris, can now interact more effectively with the organizing ring system. Their gravitational fields begin to sculpt and shape the evolving rings, creating the first hints of the complex structure that characterizes Saturn's rings today. The largest moon, Titan, exerts the strongest influence despite being relatively far from the ring system. Its substantial gravity creates resonance effects that prevent ring particles from occupying certain orbital distances from Saturn. These resonance zones become the first gaps in the ring system Myers regions, where gravitational interactions with Titan make it difficult for particles to maintain stable orbits. Smaller moons orbiting closer to Saturn have more direct effects on the rings. Some act as shepherd moons, their gravity corralling ring particles and preventing them from spreading too widely. Others create narrow gaps by clearing particles from their immediate orbital neighborhoods. Still others generate density waves that propagate through the ring system like ripples on a pond, creating the intricate spiral structures visible in high-resolution images of modern Saturn's rings. The interaction between ring particles and moons is not one way. While the moons shape the rings through their gravitational influence, the rings also affect the moons. The gravitational pull of the massive ring system can slowly change the orbits of smaller moons, causing them to migrate inward or outward over millions of years. This creates a complex, evolving system where rings and moons continuously influence each other's development. Some of Saturn's current moons may actually be products of this ring evolution process. When ring particles accumulate in gravitationally stable regions, they can gradually build up into larger and larger objects. Over millions of years, this accretion process might create new moons directly within the ring system. These moons would then go on to influence the further evolution of the rings, creating a feedback loop between moon formation and ring dynamics. As millions of years pass, the ring system continues to evolve. New gaps open as gravitational resonances with moons slowly clear certain orbital regions. The edges of rings become sharper as shepherd moons refine their gravitational control over ring particles. Collisions between particles continue to break down larger fragments and modify the system's overall structure. The rings also begin to exhibit more complex dynamical behavior. Density waves, created by moon resonances, propagate through the ring system, creating spiral patterns that wind around Saturn like the grooves on a phonograph record. Bending waves, caused by moons with tilted orbits, create vertical corrugations in the ring plane. These wave phenomena give the mature ring system much of its intricate beauty and complexity. Throughout this evolution, ring material is constantly being lost and replenished. Particles at the inner edge of the ring system eventually spiral into Saturn's atmosphere, destroyed by atmospheric friction and tidal forces. Material at the outer edges can be ejected from the system entirely, either through collisions or through gravitational interactions with moons. But new material is also added to the rings. Comets and asteroids occasionally crash into Saturn's moons, creating debris that can be captured by the ring system. Some of Saturn's moons have active geological processes, like the geysers on Enceladus, that continuously inject new particles into the rings. This ongoing exchange of material helps maintain the ring system even as individual particles are constantly being created and destroyed. The timescales involved in all these processes are almost incomprehensibly long from a human perspective. The initial breakup of the lost moon might have taken just days or weeks. The collisional evolution that organized the debris into a coherent ring system required thousands of years. The gravitational sculpting by moons that created the detailed ring structure we see today has taken millions of years and is still ongoing. And yet, by cosmic standards, Saturn's rings are remarkably young. The evidence for this comes from several different sources, but one of the most compelling is the ring's surprising purity. Saturn's rings today are made almost entirely of water ice, with only tiny amounts of rocky material mixed in. This high purity tells us something important about the ring's age. If Saturn's rings were truly ancient and billions of years old, dating back to the formation of the solar system, they should be much dirtier. The solar system is full of dust and small debris, and this material constantly rains down on everything in the system, including Saturn's rings. Over billions of years, this contamination should have significantly darkened the rings and reduced their ice content. The fact that the rings remain so pure suggests they are geologically young, probably only 100 to 400 million years old. This means the destruction of the lost moon that created the rings happened relatively recently in cosmic terms, when the first complex multicellular life was evolving in Earth's oceans. Saturn may have been a naked giant, spinning alone in the outer darkness without its magnificent crown. There's another piece of evidence that supports this young age estimate. The Cassini spacecraft, during its remarkable 13-year mission studying Saturn, was able to measure how fast ring material is currently falling into Saturn's atmosphere. The rings are not perfectly stable, they're slowly spiraling inward, raining down onto Saturn's clouds at a measurable rate. By measuring this rate and working backward, scientists can estimate how long it would take for the entire ring system to disappear. The answer is troubling from the perspective of anyone who loves Saturn's beauty. At the current rate of loss, the rings will be completely gone within 100 to 300 million years. If the rings were billions of years old and had always been losing material at the current rate, they would already be gone. The fact that they still exist suggests they formed much more recently, but probably within the last few 100 million years, and possibly much more recently than that. This paints a poignant picture of Saturn's rings. They are not eternal features of our solar system. They are temporary, beautiful, and ultimately doomed. We happen to live at the one brief moment in cosmic history when Saturn wears its magnificent crown. A few 100 million years from now, future astronomers, if they exist, will look at Saturn and see a naked giant bereft of the rings that make it the most beautiful world in our solar system today. But let's return to that moment of destruction, that cosmic catastrophe that gave birth to such ephemeral beauty. Try to imagine the lost moon in its final moments as a coherent world. For hundreds of millions of years, this world had its own geography, its own geology, its own unique characteristics that distinguished it from every other object in the solar system. If the lost moon had possessed oceans, which it might have, in its early days when radioactive decay in its core provided internal heat, those oceans would have risen and fallen in tides far more dramatic than anything we experience on Earth. Saturn's immense gravity would have raised tides hundreds of meters high, creating a dynamic, ever changing seascape across the moon's surface. If it had possessed an atmosphere, which is less likely given Saturn's strong gravitational field that would tend to strip away atmospheric gases, that atmosphere would have experienced weather patterns unlike anything in the inner solar system. Storms driven by tidal heating and Saturn's gravitational effects might have raged for millions of years, sculpting the moon's surface through processes we can barely imagine. The moon's surface would have been a museum of solar system history. Ancient impact craters would tell the story of the great bombardment that affected all the planets and moons billions of years ago. More recent craters would record the ongoing reign of comets and asteroids that continues to this day. Geological formations would preserve evidence of the moon's internal evolution. Perhaps ancient lava flows from a time when the moon was geologically active, or vast ice plains formed when ancient oceans froze solid. All of that geological and climatological history came to an end when the tidal forces became too strong to resist. In the space of days or weeks, hundreds of millions of years of accumulated history was erased, transformed from a coherent geological record into a chaotic stream of tumbling debris. But in another sense, that history was not destroyed. It was transformed. Every fragment that broke away from the lost moon carried with it a piece of the moon's story. The rocky core material that now orbits as part of Saturn's rings still bears the chemical and isotopic signatures of the moon's formation and early evolution. The ice that makes up most of the ring system still carries within its crystal structure the evidence of ancient geological processes. When scientists study the composition of Saturn's rings today, they are in a sense studying the remains of the lost moon, the relative abundances of different chemical elements, the isotopic ratios that reveal formation conditions, the physical properties that speak to billions of years of geological evolution. All of this information is preserved in the countless fragments that now orbit Saturn. In this way, the lost moon achieved a kind of immortality through its destruction. Rather than remaining a single isolated world orbiting in the outer darkness, it became distributed throughout one of the solar system's most beautiful and extensively studied systems. Every observation of Saturn's rings is also an observation of the lost moon. Every photograph that captures the ring's ethereal beauty also preserves an image of the moon's scattered remains. And what remains those are the ring system that formed from the lost moon's destruction is one of the most complex and beautiful structures in the entire solar system. Modern spacecraft observations have revealed it to be far more intricate than early astronomers ever imagined. The rings are not solid structures, as they appear from Earth based telescopes, but collections of countless individual particles, each following its own independent orbit around Saturn. The particles range in size from tiny dust grains smaller than the particles in cigarette smoke, to boulders the size of houses or even mountains. Most are made of nearly pure water ice, though some contain rocky material that gives them a slightly different color and reflectivity. Despite containing billions upon billions of individual particles, the rings maintain a remarkable degree of organization. They form distinct bands separated by gaps, with sharp edges maintained by the gravitational influence of shepherd moons. Within the major ring divisions are hundreds of narrower ringlets, each with its own distinct properties and dynamics. The rings are also extraordinarily thin for their vast extent. While they stretch outward from Saturn for hundreds of thousands of kilometers, roughly the distance from Earth to the Moon, they are typically only a few tens of meters thick. This makes them proportionally thinner than a sheet of paper and far more fragile than their impressive appearance might suggest. Within this thin disk, the rings display an incredible variety of structures and phenomena. There are spiral density waves generated by gravitational resonances with Saturn's moons, creating patterns that wind around Saturn like the grooves on a phonograph record. There are radial spokes that appear and disappear in the rings on timescales of hours, their origin still not fully understood despite decades of study. There are braided ringlets where particles seem to weave in and out of complex, intertwining paths. There are eccentric rings that maintain elliptical rather than circular shapes, despite the tendency of collisions to circularize orbits. There are regions where the ring material clumps together into temporary aggregations, and other regions where it spreads out into tenuous, nearly invisible sheets. Some of the most fascinating ring features are the so-called propeller structures, small clearings, and disturbances created by moonlets embedded within the rings themselves. These moonlets are too small to be seen directly by spacecraft cameras, but their gravitational influence creates characteristic patterns in the surrounding ring material that look like airplane propellers when viewed from above. The discovery of these propeller structures was one of the most exciting results of the Cassini mission. It showed that even today, billions of years after the original moon's destruction and hundreds of millions of years after the ring's formation, new moons are still being born within Saturn's rings. These moonlets represent a kind of ongoing creation process where ring particles gradually accumulate under their own gravity to form larger and larger objects. Most of these moonlets remain small, probably no more than a few kilometers across, but over millions of years, some might grow large enough to clear significant gaps in the rings and become true moons in their own right. In this way, Saturn's rings serve not just as the graveyard of the lost moon, but as a nursery for future generations of satellites. The rings also interact constantly with Saturn's magnetosphere, the region of space dominated by the planet's magnetic field. Charged particles trapped in Saturn's magnetic field rain down onto the ring particles, gradually sputtering away atoms from their surfaces and creating a tenuous atmosphere around the entire ring system. This sputtered material sometimes forms new, extremely faint rings at greater distances from Saturn. Some ring particles become electrically charged through this interaction with Saturn's magnetosphere. These charged particles can then be influenced by magnetic as well as gravitational forces, leading to complex dynamics that scientists are still working to understand. The interaction between electromagnetic and gravitational forces in Saturn's rings creates a natural laboratory for studying fundamental physics under conditions impossible to reproduce on Earth. The seasonal variations in Saturn's rings provide another layer of complexity to the system. Saturn's axis of rotation is tilted relative to its orbital plane around the Sun, just like Earth's axis is tilted. This means that Saturn experiences seasons, although each season lasts about 7 Earth years due to Saturn's much longer orbital period. As Saturn moves through its orbit, the angle at which sunlight strikes the rings changes dramatically. When Saturn's north pole is tilted toward the sun, the northern face of the rings is illuminated while the southern face lies in shadow. About 15 Earth years later, when Saturn's south pole is tilted toward the sun, the illumination is reversed. These seasonal changes affect the thermal properties of ring particles, causing them to expand and contract slightly with temperature variations. They also affect the visibility of fine ring structures, as the changing illumination angles reveal features that are invisible at other times. Some of the most spectacular images of Saturn's rings have been taken when the sun angle is low, creating dramatic shadows that highlight the three-dimensional structure of the ring system. The rings also create their own weather. In a sense, the complex gravitational interactions between billions of particles lead to collective behaviors that resemble fluid dynamics, even though the rings are made of discrete solid objects rather than continuous fluids. Density waves propagate through the rings like sound waves through air. Disturbances created by meteorite impacts spread outward like ripples on a pond. Temperature variations across the rings create convection like motions where warmer particles tend to move vertically while cooler particles sink toward the ring plane. These thermal effects, combined with the gravitational stirring caused by embedded moonlets and the influence of Saturn's moons, keep the ring system in a constant state of gentle agitation. All of this complexity, the intricate structure, the ongoing evolution, the electromagnetic interactions, the seasonal variations, the embedded moonlets, the wave phenomena, use arose from what was fundamentally a simple event billions of years ago. A moon wandered too close to its planet and was torn apart by tidal forces. This is a profound reminder of how the universe creates extraordinary beauty and complexity from apparent destruction. The violent death of the lost moon gave birth to one of the most elegant and scientifically fascinating systems in our solar system. Chaos self organized into intricate patterns. Destruction became the foundation for ongoing creation. This transformation speaks to one of the deep principles underlying cosmic evolution. The universe has a remarkable tendency to create order from disorder, to build complexity through apparently destructive processes. Stars are born from the collapse of gas clouds. Planets form from the violent accretion of countless smaller objects. Life itself arose from the chemical chaos of the early Earth. Saturn's rings represent perhaps the most beautiful example of this principle in our solar system. They show us that destruction and creation are not opposite forces, but different aspects of the same fundamental process. The lost moon had to die for the rings to be born. The rings will themselves eventually die, raining down into Saturn's atmosphere. But while they exist, they represent one of the most sublime achievements of natural processes operating over cosmic time. And the story is not over. Saturn's rings continue to evolve today, shaped by the same forces that created them billions of years ago. New moonlets are still forming from ring material. Existing structures are still being modified by gravitational interactions with Saturn's moons. The rings are still slowly spiraling inward toward their eventual destruction in Saturn's atmosphere. In a sense, we are witnessing the rings in the middle of their story rather than at its end. They have already experienced billions of years of evolution from their chaotic birth in the debris of the lost moon, but they still have hundreds of millions of years of evolution ahead of them before their final disappearance. This gives Saturn's rings a quality that is both magnificent and melancholy. They are not permanent fixtures of the cosmos, destined to orbit Saturn forever. They are temporary sculptures, carved by gravity and time from the remnants of a destroyed world. We are privileged to exist during the brief cosmic epoch when they grace our solar system with their presence. The improbability of this cosmic coincidence is staggering. If intelligent life had evolved 500 million years earlier, it would have looked at Saturn and seen a naked giant spinning alone in space. If civilization had arisen 500 million years in the future, Saturn would again be ringless, its magnificent crown long since dissolved into the planet's atmosphere. But here we are, existing at precisely the right moment in cosmic history to witness one of the universe's most beautiful creations. The timing is extraordinary, the beauty is ephemeral, the story is nearing its end, cosmically speaking, but we are here for what might be considered the climactic scenes. And what scenes they are! Every image returned by spacecraft visiting Saturn reveals new aspects of the ring's beauty and complexity. The Voyager missions of the 1980s first showed us the ring's intricate structure in detail. The Cassini mission, which orbited Saturn from 2004 to 2017, revealed phenomena and structures that astronomers had never imagined. Future missions will undoubtedly discover still more wonders hidden within the ring system. Each new discovery adds another chapter to the story that began with the destruction of the lost moon. We learn more about how ring systems form and evolve. We gain new insights into the fundamental physics of gravitational interactions. We develop a deeper appreciation for the complex beauty that can emerge from apparently simple processes. But perhaps most importantly, we gain perspective on our own place in the cosmos. We are made of the same materials that formed the lost moon and now make up Saturn's rings. We are governed by the same physical laws that destroyed one world and created another kind of beauty entirely. We are part of the same cosmic story of creation and creation again. The atoms in your body were forged in the nuclear furnaces of ancient stars, scattered into space by stellar winds and supernova explosions, and eventually incorporated into the planets and life forms of our solar system. In a very real sense, you are made of star stuff, connected to every other object in the universe through the shared history of cosmic evolution. The carbon in your muscles, the calcium in your bones, the iron in your blood, all of these elements were created in stellar cores and dispersed through the galaxy over billions of years. Some of those same elements might now be orbiting Saturn as part of its magnificent rings, having followed a different path through the cosmos, but sharing the same ultimate stellar origin. This connection runs even deeper. The gravitational forces that tore apart the lost moon are the same forces that hold you to Earth's surface. The electromagnetic interactions that bind ring particles together in temporary aggregations are the same forces that hold the atoms of your body together. The thermodynamic principles that govern the ring's evolution also govern the metabolic processes that keep you alive. You exist within the same physical framework that created Saturn's rings. You are subject to the same natural laws, made of the same fundamental materials, shaped by the same evolutionary processes, just on a very different scale and over very different time periods. In studying Saturn's rings, we are in a sense studying ourselves and our place within the cosmic order. And that brings us back to where we started, with you, lying in bed, listening to the story of how Saturn got its rings. You are a temporary arrangement of star forged atoms that has somehow become conscious enough to contemplate the origin of planetary ring systems. You are matter that has learned to wonder about matter, energy that has gained the ability to reflect on energy, time that has developed the capacity to think about time itself. Like Saturn's rings, you are a temporary but extraordinary creation of cosmic processes. Your existence, like theirs, is improbable and beautiful and ultimately finite. But unlike the rings, you have the capacity to appreciate beauty, to seek understanding, to find meaning in the vast scales of space and time that dwarf individual existence. Tonight, as you drift toward sleep, Saturn continues its ancient rotation in the outer reaches of our solar system. Its rings continue their eternal dance, billions of particles following their individual orbits while maintaining the collective patterns that make them one of the most beautiful sights in the cosmos. Some particles collide and break apart, others stick together to form larger aggregations. New moonlets slowly accrete from ring material while others are torn apart by tidal forces. The same processes that began with the destruction of the lost moon continue today, just as they will continue long after you and I and all of human civilization have become part of cosmic history. The universe is patient beyond human comprehension, operating on timescales that make human lifetimes seem like brief flickers of consciousness in a vast cosmic night. But for this moment, this brief cosmic moment, you exist alongside Saturn's rings. You live in the same universe as that magnificent crown of ice and starlight. You are made of elements that were created in the same stellar processes that created the materials now orbiting Saturn. You are connected to this cosmic story, not just as an observer, but as a participant in the same grand evolutionary process that creates and destroys and creates again across billions of years. As you settle into sleep, know that the rings are still there, still dancing their ancient dance around Saturn. The shepherd moons are still maintaining their gravitational watch, preventing ring particles from spreading too widely or falling too quickly toward the planet. The density waves generated by Saturn's major moons are still propagating through the ring system, creating spiral patterns of breathtaking mathematical beauty. The propeller features created by small embedded moonlets are still opening and closing as these tiny worlds migrate through the rings. The seasonal variations caused by Saturn's tilted axis are still modifying the thermal properties and visibility of ring structures. The electromagnetic interactions between ring particles and Saturn's magnetosphere are still sputtering atoms from particle surfaces, creating the tenuous atmosphere that surrounds the entire ring system. All of this cosmic activity continues, whether you are awake to contemplate it or asleep and dreaming of other things. The universe does not require your attention to maintain its operations, but somehow, the fact that you can direct your attention toward these cosmic processes, that you can find wonder and beauty in them, that you can use them to gain perspective on your own existence, somehow that seems to add something meaningful to the universe's ongoing story. Perhaps consciousness itself is the universe's way of becoming aware of its own beauty. Perhaps minds like yours are how the cosmos develops the capacity to appreciate its own magnificent creations. Perhaps the emergence of beings capable of wonder and understanding represents a kind of cosmic awakening where the universe begins to know itself through the consciousness of its own evolved components. These are deep philosophical questions without easy answers. But lying there in the darkness, contemplating the destruction that created Saturn's rings and the temporary nature of their beauty, you might find some comfort in the possibility that your capacity for wonder is itself a meaningful part of the cosmic story. The lost moon that died to create Saturn's rings will never be conscious of the beauty that arose from its destruction, but you can be conscious of it. You can appreciate it. You can find in it a source of perspective and peace and connection to something larger than the immediate concerns of daily life. And perhaps that is enough. Perhaps the ability to step outside of human scale worries and contemplate cosmic scale beauty is one of consciousness's greatest gifts. Perhaps the peace that comes from understanding your place within the vast context of space and time is reason enough to tell and retell these stories of cosmic evolution. Wherever you are in the world tonight, thank you for joining me on this journey through space and time to witness the birth of one of the universe's most beautiful creations. I hope you found some wonder in this tale of destruction becoming beauty, some peace in the vast scales that put our daily troubles in perspective, some comfort in knowing that you exist at just the right moment in cosmic history to share the universe with Saturn's magnificent rings. If this gentle exploration of cosmic catastrophe has brought you any measure of tranquility, you might consider subscribing to Sleep About Science. We'll continue to explore the universe's most fascinating stories together, always with the understanding that knowledge can be a form of meditation, that wonder can be a pathway to peace, and that the cosmos has countless beautiful stories to tell those patient enough to listen. The rings will still be there tomorrow, still dancing their ancient dance around Saturn, still carrying within their countless fragments the chemical and physical memory of the lost moon that died to create them. They will continue their slow spiral toward extinction, but that extinction is still hundreds of millions of years in the future, due time enough for countless human generations to find wonder and inspiration in their ethereal beauty. Sleep well, fellow traveler through space and time. May your dreams be as peaceful as Saturn's rings are beautiful, and may you wake tomorrow with a renewed sense of your connection to the extraordinary cosmic story we are all part of. Sweet dreams.